Hello, everyone. Welcome to this presentation. My name is Luca Fancellu, and I work at Arm supporting our latest automotive platforms. Today, together with Ayan from AMD, we are going to talk about the Armv8-R MPU support in Xen. So this work has been going on since a few years now, and many people are and were involved in this. And to them, I would like to say thank you for your contribution. And I'm positive that we will make it land on Xen very soon. So I also think that this is a very good opportunity for the community to support this architecture, especially now that the focus is going more and more towards the embedded and safety critical domains. Okay, so here's a list of the key points we are going to touch today. I will focus more on the ARM64 part, highlighting few of the features that we are going to support, and I will later leave the stage to Ayan that will walk you through the Arm32. But before we start digging into the architecture details, let me spend a few words as an introduction. So across all industries, we are seeing a rapidly increasing computational demand. And this is not only about high-performance computing. This trend is now transitioning also into the safety-critical domains, such as automotive or industrial systems. So in these areas, now certified platforms are not only expected to deliver the same level of reliability, but also higher computational performance. So to meet this challenge, Arm has released a set of new IP called Automotive Enhanced that are built from the ground to deliver rigorous performance, safety, and scalability demands. And within this IP portfolio, the Armv8-R product stands out because they deliver high-performing processor specifically tailored for time-sensitive and safety-critical domains. And this mix of raw performance and the strong level of guarantees, I believe they make the perfect foundation for the system we are going to support in Xen. Okay, so the architecture, the Armv8-R AR64 architecture is very similar to the V8A. In fact, many of the registers are the same. But let's focus more on the differences. So the first one is the supported exception levels. In this architecture, only EL2, EL1, and EL0 are supported, and EL2 is mandatory. So there is not anymore EL3. Also, the processing elements, the CPU, are always in the secure state. And the only execution state supported across all exception levels is the AR64 execution state. Another big feature of the architecture is the PMSA, Protected Memory System Architecture, which is basically the MPU. So the MPU is present at EL2 and EL1. And the EL2 MPU provides both stage 1 memory protection for accesses from EL2 and stage 2 memory protection for accesses coming from EL1 and EL0. Another big feature is the introduction of optional MMU at EL1. So for the first time, we will be able to run a rich operating system based on MMU on top of a Cortex-R. Finally, so this, there is only currently one implementation of this architecture, which is the Cortex R82 and R82AE, which is a very powerful processor, which is currently being used in our latest CSS for automotive Xena as a safety island. So let's see more in details the MPU. But first of all, what is an MPU? An MPU is a device used to protect the memory. And how does it do that? So the MPU defines protection regions that are basically ranges of memory that are protected across all the address map. So everything that is within this range is protected. Everything else will generate a fault. When we talk about MPU, we will say address translation. But what is this translation? So For the MPU, the translation is just the process of flat mapping the virtual address to the physical address. So basically, they are mapped one-to-one. A protection region is defined by these elements. So a base address, a limit address, and a set of access permission and memory attributes. And in this architecture, the minimum size of a protection region is a 64 byte. And no overlapping memory protection regions are allowed. The architecture defines also a maximum number of protection regions, which is 255. But the implementation can be different. So for example, the R82 supports 32 protection regions. There is another element of the PMSA architecture, which is the background region. What is the background region? So a background region is a set of default protection regions that are implementation defined. And this background region is used, for example, when the MPU is disabled to drive the memory attributes such as cacheability, shareability, and also access permissions. MPU and virtualization. So we have already said that there is a stage 2 translation, and this means that the hypervisor can validate what EL1 and EL0 can access, and can also modify access permissions and memory attributes of these accesses. So just to summarize, the guest can't grant access that the hypervisor forbid, and the hypervisor can further restrict those accesses, but not expand them. So in this quick example, we can see the region R4 mapped on the EL1 MPU. And this region is not mapped on the EL2 MPU. And any access within that range will generate a fault on the EL2 MPU. So how these protection regions are defined in the CPU? These are defined by these registers. So they are registers inside the CPU. For a protection region in this architecture, we have PR bar and PRR, which contains the base address and the limit address, and also other fields. And there is also a selector, which is used basically to point to the region we are interested in. There are two ways to address these protection regions in the architecture. We have indirect addressing and direct addressing. Let's spend a few words about the first one. So first one, very simple. We write the protection region number inside the selector, and afterwards we read or write the protection region through the PR bar and PRR. Very easy. But we can see there is a dependency between these registers. And so well, what should we do? Does anyone know? We need to add a barrier between, yes, an ISB barrier after we write the selector and before reading or writing the other registers. And there is a catch here, because an ISB barrier flashes the pipeline. And so this can be a performance hit depending on where we are in the, in the code base. So if we are, I don't know, context switching and stuff like that. How can we address that? As I said, the architecture provides another way to do that, the direct addressing. So additional registers are provided, and we have these PR bar n, PRR n, with n that goes from 1 to 15. And with this, we are now able to address up to 16 protection regions, issuing only one barrier, as I did in this quick example. So this new register works in a way where basically they point to the protection region that whose number is formed by the upper 4-bit of the selector combined with the lower 4-bit embedded in the register itself. So EL1 MMU support. As I say, this is the first time we can run a rich operating system on top of a Cortex-R. And this feature is optional. This feature is optional, and it is advertised through this identification register. In this architecture, now we are able to run both MPU-based guest and MMU-based guest. And there is a bit inside VTCR that decides basically what guest can run on top. And we are able to show the right programming model for that guest. Let's spend a few words now about the, our roadmap for the introduction of the feature. So we define a few milestones for that. We have early boot, late boot, domain creation, and runtime. We already delivered early boot, where we basically define some data structure for tracking the MPU status. And we've also delivered some assembly code to populate these structures and enable the MPU in the early stages. We are currently supporting the late boot phase, where from the C word, we will support the full execution of the start Xen. So we will need to provide code to do the early mapping of the device tree, code to manipulate from the C word these data structures, and then we will need to wire up the Xen API, such as map pages to Xen, etc. Finally, we will upstream the implementation of the P2M and also the context switch, and we will be able to run a guest on top of this architecture. Future work, we have, for the first time, we will need to support an MPU guest. So we inherited all the code related to saving the context of an MMU guest, and now we will need to provide a way to Xen to know if we would like to start an MPU guest-based or an MMU-based guest. So we are thinking about a device tree property, for example, for the DOM zero-less setup. We will need also to provide additional data structure to save the EL1 MPU state. And also on context switch, we will need to save additional registers, one of which is VTCR, which contains that bit selecting which type of guest it is. Another piece of work is the SMP support on the architecture. So the current work is supporting only the boot CPU. So to enable SMP, we will need to provide additional data structure for each CPU. We will need to allocate this structure and basically populate the mappings from the boot CPU inside the prepare secondary MM. We will need to provide the assembly code running on the secondary core that basically takes this mapping from the data structure and copies inside the CPU. And finally, we will need to wire up a few of the memory of the functions like remove modified early mappings and free init memory, also for the secondary cores. Okay, so this ends my part of the presentation. I've prepared a quick pre-recorded demo of Xen and running Linux on top on a Cortex-R platform. So let's see if I find, yes. Okay, so the AVP is starting. Xen is starting, and now we are copying the kernel. So these steps takes a while, so I will, okay. So now the kernel is put in the static bank, static memory bank. And here we go, we are running Linux. I will skip part of the boot just to show. Okay, yeah. And we are in the user space. All right, Ayan, now the stage is all yours.
Hi, My name is Ayan, and I'm working with Luca on this MPU upstreaming work that has been going on. So one of the real benefits of working in open source is that we can collaborate with each other, and my work relies on most of the hard work that's being done by Luca over the past year. So the differences between the 32-bit and the 64-bit is very minimal. So in the case of 32-bit, you only have the PMSA, that is the protected memory state architecture supported in EL1. So that means that you cannot run any MMU based guests in EL1. That's the very critical difference between the two. Other than that, there are some register naming differences and all. And the other difference is, since it's a 32-bit architecture, so it's like you can map up to 4 GB. So you can actually map the entire RAM. Now, one thing that we are working on is, in the case of 32-bit, we have tried to, let's say, have the entire static memory mapped. Now, of course, like if you remember Alejandro's talk yesterday, it was like it can lead to speculative accesses. And that's something that we are thinking like how to address, because r in the case of R52, you have a safety critical system which will only run minimal set of VMs in the EL1 mode, and it will be like each VM will be tied to a particular core. So do we really need to have a dynamic memory mapping for the domains in the case for EL2? That's something that we are working it out. So one thing is, why did we choose like an upstream first approach? So ever since this work was started by Penny in ARM, so we decided that we want to collaborate in the upstream because it's a very new architecture. And within AMD, if you have seen the embedded world demo last year, so AMD released that AI Versal Gen 2, and a part of it is that we have the RPU cores, R52 cores. So we definitely need to have Xen hypervisor support for the R52. So that's when we said that, okay, since ARM is developing the R64 port of it, let's get together and we can work on this together in the community. And that also means that when we work in the community, we can leverage the expertise of the Xen experts who have pioneered development of the of ARM in the upstream in the upstream. Now, one good thing is this has really been a good work between both the organizations. And the way we have worked is that whenever like Luca or ARM is sending out the series, we at AMD, we try to test it so that it works also for the R52 parts, and the corresponding bits we send it to upstream. So we are absolutely working in like the lockstep mode, the thing that you would imagine like in a safety critical system. The other the So when we look back at it, like around 3 years back when we started this effort, it was around like 150 patches that we had, and it was all downstream. And then we got together and we said that, okay, how do we break it down? So this has been the entire flow of the work that has gone in. So we started with the gig v3 support for the arc32, then the 32-bit physical address. Then we tried to pull out the MMU specific bits, because what happens is that since Xen is traditionally been built on the MMU based systems, so it's kind of tightly coupled, the MMU registers, the page tables and everything. So we wanted to extract that out so that we can plug in the MPU based functions over there. And from there on, like we decided that we will, first we will upstream the early boot support, then the late boot support. So that's how it has been going on. And if you sorry and if you see, in the last 1 year, we actually made very good progress with Luca's team, and we got almost like 40 plus patches that's out there. So the good thing is, if you today want to take a fork of Xen from the upstream, you can see Xen getting booted on the R52 cores, uh, and also on the R82. So the other cool thing is, like like Xen, it doesn't work in isolation. So in order to validate this, you need you need a VM and you also need an emulator. Now, of course, like we have the FVP, which we have used for working, but we also ensured that we have this support for R52 in the QEMU as well. So today, if you take the QEMU from the upstream, you can run run Xen on top of it. And we also have support in Zephyr. So Zephyr, the RTOS, it has also support for the R52 and the R82. So you could see we have all the bits and pieces that's out there in the community, and the final piece is just to get Xen working and booting, and as Luca mentioned in the plan. So we are going ahead with that, and hopefully, Mark, that will make things easier for you once we get everything upstream, and that's how it's going on. I have a demo, but maybe I'll to save some time, I can show the demo to people who are interested. But I would like to take any questions if you have.
I have a question about the MPU architecture. So what kind of exception is triggered in case of MPU violation? Does it have any exception class or ESR register, FAR, that kind of registers are provided? Mm-hmm. So we will have any syndrome registers that show the exception class. Okay, thank you.
So great work. Thank you, Luca and Ayan. So I think this slide deck shows a lot of requirements. We're really kind of discussing them. Anderson's question about what's the ERC that gets fired, absolutely critical for safety requirements. You have to take that ERC, you have to cover that ERC. What are you going to do? And the design about what are you going to do when you hit that ERC is safety critical. There are even more detailed requirements that I'm kind of curious about. When I saw the code the first time, the cell register, where you select every 16 or so, like the ISB, I was like, oh, the ISB is terrible. We just need to direct. But it does, I noticed that there's a lot of code that's doing the switch, and it's keeping track of the last cell that was written and all to reduce the ISBs. Is it possible to direct access all 64 or all bunch of them? And if not, why not? Have we talked with ARM about this? Thanks.
Oh, and because the number of protection regions are implementation defined, maybe, where is it? Oh, okay, sorry, I skipped that. Yeah. So probably probably there is also the need to somehow reduce the cost. So the more registered. Yes, exactly. So there are a lot. So in Harder might be costly. I don't know. This is more a question for Harder people.